So first off, to define Fourier series, a Fourier series is simply just an expansion of a periodic function, or even any function in general, in terms of infinite sums of sine and cosine terms. Fourier series can be helpful when you're trying to model functions that you don't necessarily know the equation for, such as the square wave, which looks like this over here, as well as other functions such as the triangle, the sawtooth, and the half sine wave, although there are many more examples. As you can see in this first picture up here with the red and blue graphs, there's a sinusoidal function that is trying to model the square wave. However, just by looking at this, you can tell that this is not a good approximation of the square wave, and this is where Fourier series comes into play. As you add up more terms in your Fourier expansion, the waves begin to better approximate the square wave, as you can see in these successive pictures. As you can see in this last picture, this is a much better representation of the original square wave than this one right here, the first one. So as you can see, as you add up more sine and cosine terms in your expansion, the more accurately it represents a periodic function. Fourier series, they shouldn't be confused with something called Fourier transform, although they're very similar. Fourier transform is basically where a time signal is broken up into its frequencies using exponential functions, although they're still very similar topics. Fourier series can be used to solve complex differential equations and to represent any periodic function in general. They also have important applications in physics and electrical engineering. For example, in circuits, which we are actually learning about in AP Physics right now, which is cool. Basically, Fourier series, they can model the voltage of a capacitor using expansion of terms. In addition, Fourier series can also be used to analyze and process sound waves and noise, and this is we will talk more about this in later slides. And what we have here is basically what I talked about in the previous slide, which is where when you add more sine and cosine terms in your Fourier expansion, the frequency of the function increases, and this is what allows the Fourier series to better approximate whatever periodic function you're trying to model.
Before exploring what Fourier series are more in depth, let's look at who they came from. Jean-Baptiste Joseph Fourier, it was this droopy man seen below. Fourier was the founder of Fourier series when he was searching for a solution to the heat equation, where the heat equation is an equation made to describe the distribution of heat in a metal. The very simple explanation of how he arrived at this solution is that it was known that simple heat sources behaved in ways that could be represented with sine and cosine functions, so for complicated ones he thought you could just use more of them. Delving into the math of Fourier series. As we can see, the Fourier series and the Taylor series are rather alike. Both are made up of infinitely many small terms, each one smaller than the next. The more terms we have in this series, the more accurately we are able to replicate the original functions or graphs. The primary difference between these two is that one of them, the Fourier series, uses trig oscillating functions to represent the series, while the other relies on the idea that the more similar the differentiated versions of the functions are, the more similar is the original function. Another difference is the fact that there are two infinite sums to the Fourier function as compared to the singular one in the Taylor series. This only works when the Fourier series even converge. To find the first term in the Fourier series, aka the constant, we can take the integral of the series from negative pi to pi. The reason that we can do this is that all the infinite series rely on trig functions that cancel out over this period. For cosine, this will be canceling out of equal terms, which makes 0, while for sine, it's an odd function and therefore also cancels out. As for finding the a0th term, we can simply take the integral of a0, which will leave us with 2 pi times a0. Following this, if we can take the integral of the Fourier function, we will be left with that exact value previously mentioned. Understandably then, we can simply divide the integral of the Fourier function by 1 divided by 2 pi to the left with solely a0, giving us the constant we were looking for.
So we're going to be looking at how to find coefficients for cosine terms. So what you do to a Fourier series is that you multiply everything by cosine m of x, where m is an is an integer. So you can recall from previous that the first integral just equals to 0, and the second integral produces two different results depending on what n and m equal. So let's just say that n equals to m. So we can rewrite the integral like this, and then we can use a trig identity in order to simplify everything and get pi times a sub n. In order to isolate a sub n, divide both sides by pi in order to get the coefficient like this. And then we have a situation where n does not equal to m, and you can rewrite the integral using a product to sum trig identity. And then after that, you can use integral properties in order to split everything in half. And you can see here we have cosine of m minus n of times x. And when m, just an integer, minus n, just an integer, that just equals to an integer. And as we've established, the integral from negative pi to pi of cosine of an integer of x just equals to 0. And same thing with m plus n. And then for the third term, we can just use product to sum trig identities again. And we have sine of an integer plus an integer of x. We've already established that that equals to 0. And you can do the same thing with m minus n. In order to find coefficients of sine terms, you just multiply everything by sine of m of x. And then this just equals to 0. As you can just recall, this just equals to 0. And we have another situation where n can equal to m, or they cannot equal to each other. So when you have n equals to m, you can just rewrite everything like this and do some totally trivial engineering math. And we have a situation where n does not equal to m. Then we could just use product to sum trig identities again. And then just get this, which, as you can recall, just equals to 0.
Bernoulli's formula for integration by parts. Bernoulli's formula for integration by parts comes in handy when integrating expressions in Fourier series, because most of the time when trying to solve for an and bn, aka any term of the sine part and any term of the cosine part, you will result in applying the uv integral of v du multiple times, and Bernoulli's formula can save a lot of time. Bernoulli's formula can be seen down here in this part.
Okay, so one application of Fourier series is in sound. So, for example, we can take music. Fourier series and analysis can be used in synthesizers, which rely on different combinations of frequencies and sine and cosine functions in order to reproduce sound waves of any musical instrument. Since sound waves are waves, Fourier series can be used to emulate different sounds. So sounds are made by such waves that you often hear in 8-bit music, like in video games. Modifying the amplitude and frequency of the wave can change how we hear them or how we perceive them. A higher frequency is a higher pitch, and a higher amplitude is a louder sound. Take the square wave, which is below on the left. This wave can be visualized right here. As we add more terms, a Fourier series can turn the trig function, which is on the right, closer and closer to the original function. This creates a polynomial approximation. So as we see, as we add more terms, the trig function, which starts out as red, becomes more and more accurate and starts to look more and more like the square wave that we started with. This creates an approximation, and as we add terms, it becomes more and more like that square wave.
Hi, so now we're going to be doing a Tetris demo, and we're really going to be demonstrating a cool application of Fourier series in music.
Below, we have our plot wave function. It essentially just takes a sample and it will plot it using matplotlib. That sample is generated by this function, generate sine wave. You want to talk about that?
Yeah, sure. So basically, this function takes in sample rate, time, frequency, amplitude, and a Boolean that basically says whether or not the sine wave will be plotted. Sample rate essentially means how many data points are sampled per second. So a higher sample rate will yield a more accurate visualization, whereas a lower sample rate might not look good at all. And then we all know what time, frequency, and amplitude are. Those are just what specify our sine wave.
We're using frequency in hertz and time is in seconds. As you can see here, we call that function and it uses the plot wave as the Boolean is set to true. So as you can see, we generate a wave here. If we want to change the frequency, for example, we can just change the third parameter as frequency is the third parameter. Let's say we want to make the frequency 5 instead of 10. We just run that, run the cell, and then there you go. You can see that the graph changes. From that, we made a function called play sine wave. It essentially just creates that wave. It generates that wave that it takes that as a parameter, and it plays that wave back to you in the audio format using sound device, like Audit talked about. It uses 44.1 hertz because that's a frequent like audio playback standard, I guess. So here you can see we can play that sine wave right back to us.
Cool. And now we're going to be introducing the application of Fourier series in sound. So again, we've already done a brief overview of this, but Fourier series are really a novel approach in dealing with sound and sound waves. Much like Taylor series, as we add more terms to our polynomial, our approximation becomes more and more accurate. So below in this cell, we're going to be plotting a sawtooth wave, and we're going to be plotting a number of Fourier approximations. And we can see that as we add more terms, our approximation is going to be better and better. So Nevin can demo that.
So as you can see here, we just generate a sawtooth wave, and that's what we call the wave here. And then we generate two Fourier series, one with 10 terms and one with 30 terms, and then we plot them. Let's see what happens when we run this code. So as you can see here, we create a graph, but as we add terms, it gets more and more accurate. This blue function right here is the original saw function, and this green and orange approximations are just approximations. As you can see, the 10-term approximation is not very good because it doesn't use that many terms of the Fourier polynomial. Much like Taylor polynomials, it's not very accurate when you don't have enough terms. As we add terms, we go up to 30 terms, it gets a lot closer to the original function. If we went up to something like 10,000 terms, it would be almost like virtually identical to the original function. Next, we're gonna give a little bit of a demo using Tetris audio. So here's a little audio clip from the Tetris song.
Now that we've listened to the Tetris sound, we can actually talk about how we can use Fourier series to sort of approximate the Tetris waves. So what we did was we split up this short audio that we just listened to into its constituent notes, and each note represents a periodic function. Although there is some background noise, they're still pretty much periodic. And from this, we can sort of take the Fourier series of each periodic function, each note, and then append them all together. And from that, if we add enough terms, theoretically, we should be getting an approximation that we could listen to that sounds almost exactly like what we just listened to.
So if we just take a look at the code quickly, you can see that we convert a wave file, which is just an audio file, into an array using NumPy. This array will be able to turn into like visualizations and whatnot. Then we set up the approximations. You can see we have 3 different approximations here. The first one is 40 terms, the second one is 400 terms, and the last one is 10,000 terms. So it's most likely we believe that the 10,000 term approximation is going to be the most accurate. So generally we just get this audio data here, and then we play this series as well as graph it. So let's run that. So from that audio, becomes pretty clear which one is the most accurate one. The first one sounds horrible, not even close to the original song. The second one sounds very muffled and not quite accurate. And the third one almost sounds exactly like the song because of how many terms we use.
And here, you can see our visualization that we used Matplotlib for. And it's really clear that as we add more terms, our approximation gets better. You can see the legend where red is 40 terms, and it's really not approximating the function at all. But once we get to 10,000 terms, and even 400 terms is a pretty close approximation, but by 10,000 terms, it's almost indistinguishable from the original wave. Great, so I hope you enjoyed that Tetris demo. And you might be thinking that this is cool and all, but why would we ever want to use Fourier series to approximate sounds or do other tasks of this nature? But actually, many real-life applications do use Fourier series for similar purposes, and one such application is Shazam. And Shazam is a modern sound recognition tool that is built into Apple's iOS. And essentially what you can do is you can upload any audio or any sound input from the mic, and Shazam will be able to identify what song that you have sort of recorded. And it does this using something called Fourier transform. So basically, two main physical characteristics of sound are frequency and amplitude. And Fourier transform is similar to Fourier series. It transforms sound waves into a graph of frequencies that the sound is made of, and it also breaks it down into their constituent intensities. So the difference between Fourier transform and Fourier series is that Fourier transform can be used to represent any general non-periodic function rather than simply periodic functions. And Shazam uses something called fast Fourier transform, which is an algorithm that is able to do this really quickly for sound waves. So Shazam is just one of the very cool applications, and I'm just going to sort of like walk through the steps that Shazam takes. So basically, it takes a few steps really simply. One, obviously, we record the song by our phone's microphone. Two, we convert the audio that we recorded to a frequency domain. Shazam also uses a spectrogram to create an audio footprint. And then finally, that fingerprint using the spectrogram and Fourier transform is matched to a sample in their database. And yeah, that's how Shazam works. And Fourier series basically just have many applications. Sound and Shazam are just one of them.